In this section, we will discuss matrices. Singular is matrix and plural is matrices. They have many applications, but to start with, we can think of a rectangular array of numbers. An example, matrix A may be 1, 2, 3, 0. We use either large round brackets or large square brackets to denote the matrix. We say that this matrix has 2 rows and it has 2 columns. And one particular entry of the matrix is written A sub ij. The matrix is usually denoted by a capital letter and the entries by a small letter with 2 indices. Actually, we should write some separator here, some semicolon or something like that. This ij is not multiplication, this is not I times j. But usually we omit the separator, we omit the semicolon, and we just write it this way. So in this case, 1 is the entry 111, 2 is the entry A12, 3 is the entry A21, and 0 is the entry A22. So I specifies the row starting at 1 at the top of the matrix and going down, and the second index specifies the column starting on the left with 1 and going to the right. If the number of rows is equal to the number of columns, we say the matrix is a square matrix. Otherwise, we call it a rectangular matrix. And what operations there are for matrices? We can take a matrix and multiply by a number, by a scalar. Having this matrix 1, 2, 3, 0 multiplying by 2 gives the result 2, 4, 6, 0. In general, if we have a matrix capital A and we multiply by a scalar, by a number alpha, then the result, if we call it capital B, has entries B sub ij equal to alpha times A sub ij. That means we multiply each entry of A with this scalar. Another operation is addition of matrices. If we have, say, matrix 1, 1, 2, 3, and we have the matrix B, say 2, 0, 1, 4, we can build the sum A plus B, and this is component-wise. 1 plus 2 is 3, 1 plus 0 is 1, 2 plus 1 is 3, and 3 plus 4 is 7. So if we call it C, then Cij is Aij plus Bij. We say that the addition of matrices is defined component-wise. We just add each corresponding pair of entries. Well, and because addition of real numbers is commutative, then addition of matrices is also commutative. Now, let's have a look at a completely different, much more complicated operation, namely multiplication of matrices. If we take these 2 matrices, we can multiply them. Let's write it once again, 1, 1, 2, 3, times 2, 0, 1, 4. Unfortunately, multiplication of matrices is not defined component-wise. It is not just matrix of the corresponding products of corresponding entries. We could define this operation, but it has almost no application. The multiplication is defined using Scalar Product, and this has many, many applications. You remember Scalar Product? A dot B is sum of A sub I, B sub I. Now, consider one particular row from the first matrix and one particular column from the second matrix. And if the width of the first matrix, the number of columns, that means the length of the rows, equals the number of rows, the length of the columns, then we can consider the scalar product of one row with one column, and this will be the entry of the new matrix. So, the entry 1, 1 will be the scalar product of row number 1 with column number 1. That means 1 times 2 plus 1 times 1. The entry in position 1, 2 will be the scalar product of row number 1, column number 2. That means 1 times 0 plus 1 times 4. And similarly for the second row. The entry 2, 1 will be the scalar product of row number 2 with column number 1. 2 times 2 plus 3 times 1. And finally, the entry at position 2, 2 will be the scalar product of row number 2 with column number 2. 2 times 0 plus 3 times 4. Yeah. Later you don't have to write plus times, and so on. You can perform this operation just on the fly. But this time I want to write it explicitly to see what we multiply with what and what we add with what. So we have 2 plus 2 is 4. Sorry. This will be first row, the first column. 1 plus 2 plus, 1 times 1. I'm sorry. And 2 plus 1 is 3. Then we have 0 plus 4, which is 4. Then we have 4 plus 3, which is 7. And finally, 12. So, if we say you call the product C, then we can say that C sub ij is the scalar product, that means sum of the products A, I, K, B, K, J, and K runs from 1 to the common dimension, let's call it N for the moment. You see, I is the leftmost in the first index on the left, and it is the first index on the right. J is the last index on the left, and it is the last index on the right. And then we have one more index, and this appears twice in positions that are just neighbors. And we sum over k, we sum over this index from 1 to the common dimension. K does not appear, the summation index does not appear in the result. Well, surprising enough, multiplication of matrices is not commutative. Let us illustrate this by considering, say, the matrix B, which will be B times A. So B is 2, 0, 1, 4, and A is 1, 1, 2, 3. So we have 2 plus 0 is 2, and this is different. So completely independent of what the remaining results are, different results. But let me complete this. 2 plus 0 is 2. 1 plus 8 is 9, and 1 plus 12 is 13. So we see that AB is not BA. Strictly speaking, it is not true that AB is BA for all pairs of matrices. Sometimes it may be true. Say, if A is 0 matrix, all the entries are 0, then times anything is 0. 0 on the left, 0 on the right. Yes, in this exceptional case, AB is BA. Or if A is such is unit matrix. Unit matrix is a matrix that has 1 on the principal diagonal and 0 everywhere else. And if you multiply A with any matrix, you get the matrix itself. So then AB is equal to B, and BA is equal to B, and B is B. So if A is the unit matrix, then it is true that AB is BA. So in some special cases, it is true. This means it is not true for any matrices. It is not true for all matrices. It is not true for all matrices. In general, we say that AB do not commute. If for some special cases AB is BA, we say these two matrices do commute. Well, this is a special situation, not a typical one, but it may happen.